Welcome back. In this video, I want to talk about how we can use units to check to see if there is a problem with an equation. Now, before I do this, I want to just briefly talk about equations in general and how we handle all of the equations that you're going to encounter in this class. Now, probably the best bit of advice that I can give any student who takes AP Physics is the best thing you can do is internalize the equations, okay? You need to interpret the equation in your own words. Don't just think of the equation as, some bit of numbers. You have to think about it in terms of some kind of like real-world experience. Consider like a familiar example, right? And think about what happens with the example when you change some quantities. What happens when something's heavier? What happens when something's longer, right? Try to figure out how that changes the problem, okay? Then you can use that intuition that you have to check to see whether or not the answer you have makes sense. Another very good thing to do is to know where the equation comes from. Almost all of the equations that I'll give you in this class, if they can be derived, I'll show you how to derive the equation. I'll show you where it comes from. If you know where an equation comes from, you don't have to have it memorized. Anytime you need the equation, you can just derive it. In addition to these things that I've listed above, there's also limiting behavior and units. And right now I want to talk about units, and in the next video we'll talk about something called limiting behavior. So how can units help us check an equation? So this example says, while taking a test you forgot the units of force, but you remember that Newton's second law says F equals ma. So the question is, how do we use this equation to figure out the units for force? And the answer is that anytime you have an equal sign, the units on one side of the equal sign has to equal the units on the other side of the equal sign. So we have to have the same units here as we have over here. So this means that the units of force have to equal units of mass times the units of acceleration. These little square brackets here mean units. So we know units of mass are kilograms, and acceleration, I haven't talked about this yet, but hopefully some of you remember from last year. Acceleration is meters per second squared. So the units of force have to be kilogram meters per second squared. In the next example, it says, suppose we're studying the force exerted by a spring. You remember that the force is given by this formula, where delta x is the distance that the spring has been stretched. Use dimensional analysis to find the units of k. So delta x is the distance a spring is stretched. So we know that the units of delta x are going to be meters. Once again, we can do the exact same thing we did last time. The units of force have to equal the units of k times delta x. So we have the units of force equal the units of k times the units of delta x. And this time I'll have to rearrange the equation to solve for the units of k. So the units of k are equal to the units of force divided by the units of delta x. And in the previous example, we saw that force is kilogram meters per second squared. So when I divide this by meters, the meters cancel and we get kilograms over seconds squared. So this is the units for this spring constant. That's what that's called, k. Now let's look at another example. This example says, while taking a test you are asked to calculate the period t for the motion of a mass m that is attached to a spring with a spring constant k. You remember when studying from the night before that the formula for the period is either this or this, but you can't remember which one it is. So we're asked to use dimensional analysis to determine which formula is correct. Now let me briefly just talk about what a period is. So if you take a mass and you attach it to a spring, so let's consider a wall here, and I've got a spring, and I take a mass and I attach it to the spring. Now if I push this mass in one direction, the mass is going to go back and forth, and it's going to oscillate like this. The period is the amount of time it takes for the mass to go from one side all the way over to the other side and then come back to where it originally started. So the period is a measurement of time. It's how long that takes. So we know that the units of t are seconds. So since we know that the units of t have to be seconds, all we have to do is look at the right side of these equations and figure out which equation has the units of time. because both sides of the equation have to have the same units. So here we have units of time, and on this side we have to have units of time. So let's just go ahead and calculate both of them. Now, I should have mentioned, this k here that appears in this equation, this is the same k that appeared in the previous example. So this k has units of kilograms over seconds squared. That's the stiffness of a spring. The larger that is, the more stiff that spring is. So we have the units of k are kilograms per second squared, and the units of t are seconds. So let's go ahead and start with this one that's on the left. So we have that this is going to be square root of the units of k divided by the units of m. So this is the square root of kilogram per second squared divided by kilograms. So this has units of the square root of 1 over seconds squared, or just 1 over seconds. So obviously this does not have the right units. T has units of seconds, and the square root of k divided by m has units of 1 divided by seconds. So let's try the other equation. So here we have the square root of the units of m divided by the units of k, which is going to be the square root of a kilogram divided by kilograms over seconds squared. And remember that when you have a ratio in the denominator, you can move it into the numerator, by flipping the fraction. So this is going to be the square root of a kilogram times, and we'll flip that fraction, so we have seconds squared over kilograms. So when we do this, the kilograms cancel, and we have the square root of the seconds squared, which is just seconds. So we can see that this equation over here on the right has units of time, which it's supposed to, because t is supposed to have units of time. Now, in addition to these rules about equal sign, there's also rules about addition and subtraction. Anytime you add two quantities, the units of these quantities has to be the same. It doesn't make sense to say something like 1 mile plus 1 hour. What is that even supposed to mean, right? But I could say something like 1 mile plus a half a mile. That's equal to 1.5 miles. This second equation here makes sense because I'm adding two things that are representing the same quantity. I'm adding a length to a length. Whereas up here, I'm taking a length and I'm trying to add it to time. That doesn't make any sense. Now, another thing that we need to be careful about when we do addition is that you should always write both of these things in terms of the same unit. So, for example, if I took 1 foot and I add it to 1 inch, this is not just equal to 2 feet or 2 inches, okay? I can't just take the numeric value 1 and add it to the numeric value 2 to get 2, okay? Instead, what we have to do is we have to convert either the feet into inches and then take the sum, or we have to turn the inches into feet. So one way to do this would be to say I have 12 inches plus 1 inch, and that's equal to 13 inches. So this example says, when an object accelerates at a constant rate a, its velocity is given by this formula. And we're just asked to verify that this is going to have the right units. So notice in this example we have an addition sign. So this means the units of a times delta t have to have units of velocity, and that the v0 over here also has to have units of velocity. So remember that v, velocity, has units of meters per second, right? It's the speed of something. It's how quickly it's moving. So we have v final is equal to the units of v initial plus the units of a times the units of delta t. So here we have meters per second are equal to meters per second. And over here, acceleration, remember, is meters per second squared. Delta t, that's the change in time, so that's units of seconds. Notice they cancel. So we have meters per second plus meters per second. So in fact, we are adding meters per second to meters per second, and we get meters per second. So this equation works out. Now, in addition to the rules about addition and subtraction, there are also rules governing special functions. Special functions are things like sine, cosine, the exponentials, if I want to take e to the x, or I want to take a logarithm, tangent, obviously. All of these things are special functions. And anytime you have a special function, there are two rules. Firstly, the units of these functions are always going to be unitless. So if I have tangent of something, that whole thing is going to be unitless. So tangent, say for example, of k delta x, this thing here, this whole thing is unitless. In addition to that, the argument of the special function is also always going to be unitless. The argument's that thing that appears in the parentheses. So for example, if I have sine of omega t, this thing here is the argument. And my tangent of k delta x, this thing here, this k delta x, was my argument. This thing always has to be unitless, and the entire function, when we evaluate it, is also going to be unitless. So let's look at a simple example. A traveling wave in one dimension is described by this equation, where x is a position and t is time. So we're asked to find the units of k and delta x. So this means that the units of k times delta x, or I'm sorry, k times x has to be unitless. So this thing is unitless. And this thing over here also has to be unitless. So let's see what that means. So unitless, we typically just represent that as a 1 when we do dimensional analysis. So we see that 1 is equal to the units of k times the units of x. Now I know that x is a position, so it must be measured in meters. So we see that the units of k are equal to 1 divided by the units of x. So it's 1 over meters. Similarly, if we calculate the units of omega, we have 1 is equal to the units of omega times the units of time. So solving for the units of omega, we see that they are equal to 1 over the units of time, which is 1 over a second. So in this last example, we say, during a test you are asked to calculate the period of a pendulum. The pendulum is made of a mass m and is suspended from a string of length L. The mass is displaced so that the string forms an angle theta with respect to the vertical. Unfortunately, you forgot the formula for the period. So the question is, how do we use dimensional analysis to make an educated guess as to the formula for the period? So first, let me just kind of draw a picture of what's going on here. So a pendulum, this is when you hang a mass from a string. So up here we've got the wall, and then you've got the string, and then attached to that is a mass. And I say that the angle between this and the vertical is initially theta. Okay, so we've got length L and a mass m. Obviously, another variable that's going to be important here is the gravitational constant g, which is what's actually pulling this mass down to the bottom of its motion here. So how do we use dimensional analysis? Well, whatever formula we have for the period, t, actually I should have mentioned again, t is once again the period. Okay, so this is going to be the amount of time it takes for the mass starting here to swing over to the other side and then to come back to where it started. So t has to have units of seconds or time. So whatever formula we have for t, it has to have units of time. So let's just consider the most general possible formula that we can think of. So it could be some constant times theta raised to some power, let's say alpha. Actually, let me change the order of that. Let's say the mass raised to alpha times the length of the string raised to beta times gravity raised to gamma times theta raised to delta. And here I've just chosen these Greek letters, alpha, beta, gamma, and delta. They're the power that I'm going to multiply these things by. So I've got mass raised to the alpha power, L raised to the beta power, G raised to the gamma power, and the angle theta raised to the delta power. Now remember that we know that units of mass are kilograms, the units of the length of the string, that's a length, so it has units of mass, and the units of G are meters per second squared. So this thing on this right side has to have the same units as t. So this thing on the right side has to have units of time. So we have units of t are equal to, c is a constant, so it doesn't have units. It's going to have the units of mass raised to the alpha power, units of length raised to the beta power, the units of gravity raised to the gamma power, and unfortunately theta doesn't actually have units. Angles don't have units. So mass has units of kilograms, so we have kilograms raised to the alpha power. Length has units of meters raised to the beta power, and g is meters per second squared raised to the gamma power. And this whole thing has to have units of seconds. So the way that we do this is you want to rewrite the right side so that all of the units are listed separately. So we have kilograms raised to the alpha power. That's already separated. Now meters, we've got beta meters coming from this L, and then we also get meters coming from G. So the total number of meters we have is we have beta meters from L, and we have gamma meters from G. So we have meters raised to the beta plus gamma power. In time, because this is seconds squared, it's in the denominator, we could write this as seconds raised to the minus 2 gamma power. Now, the units over here have to equal the units over here, okay? So looking at this, over on the left side, we don't have any units of kilograms, so alpha has to equal 0. We also don't have any units of of meters, right? On the left side we have seconds, no units of meters, so beta plus gamma also has to equal 0. Now we have 1 unit of time on the left side, so we need to have 1 unit of time on the right side. So minus 2 gamma has to equal 1. So we have 3 equations, so we can simply solve for these now. So we have alpha equals 0, we had beta plus gamma is equal to 0, and we had minus 2 gamma is equal to 1. So using this second equation, we can see that gamma is equal to minus 1/2. Using this top equation now, if I plug this in, I have beta minus 1/2 is equal to 0. So beta is equal to 1/2, and we have alpha is equal to 0. Now if we go back to what our original equation was, it was c m raised to the alpha power, the length raised to the beta power, and g raised to the gamma power. So now I just plug in for alpha, beta, and gamma. So I have that t could be any constant. Again, we weren't able to rule out constants because they don't have units. It could be any function of theta because theta doesn't have units. But we know that it doesn't have any units of m because m is raised to the alpha power and alpha is 0. The length is raised to the 1/2 power, and g is raised to the minus 1/2 power. Or another way to write this is c f of theta times the square root of L divided by g. So I think I'm going to leave off there. In the next video, I'm actually not going to talk about mental math. In the next video, I want to talk about how we can use limiting cases, so considering extreme examples to check whether or not an equation is correct.